Alright, so let's look at the limit comparison test. Suppose that we have two series, a sub n and b sub n, and they're both positive, and the limit as n goes to infinity of a sub n over b sub n is equal to L, and L is finite and positive. Okay, it approaches a number, and it's a positive number. Then the two series either both converge or both diverge. So what we want to do is we may be given a series that's kind of messy looking, and we want to compare it to something a little simpler. And so what we can do is the one that we're comparing it to, the simpler one, we can determine if that one converges or diverges, and then if these conditions here are satisfied, then that means our original series converges or diverges, does whatever the series that we're comparing, okay, the comparison series, whatever it does, that's what our original series does, is it if as long as these conditions here are satisfied. All right, so let's take a look at an example. Okay. All right, so we've got the square root of n over n squared plus 1. Now, the series that we want to choose, what you want to do is take the term with the largest exponent from the numerator and the term with the largest exponent in the denominator, and then disregard everything else. So we're going to compare to this series. See, I kept this term because it has the largest exponent in the numerator, and I kept this n squared because it's the largest exponent in the denominator. All right, so let's rewrite this. We have square root we have summation n equals 1 to infinity of n to the 1/2 over n squared, which equals summation n equals 1 to infinity. Now, if I bring this down, I subtract the exponents. I've got 1 over n to the 3/2. And what this is a p-series now. Okay, so we can easily determine if this converges or diverges. And remember, in a p-series, it converges if p is greater than 1, and diverges if p is greater than 0 but less than or equal to 1. And you can see here, here's our p. Our p is 3/2, and it's larger than 1, so we know that our comparison series converges. All right, so now we have to take the limit as n goes to infinity of a sub n over b sub n. We have to evaluate this limit. And this series here, that's going to be our, erase that. This is going to be a sub n, and this is going to be b sub n. All right, so this is equal to, let me change colors back. This is going to equal the limit as n goes to infinity of a sub n, and this square root of n, I'm going to write that as n to the 1/2, and then I've got over n squared plus 1. So this is a sub n over b sub n, which is 1 over n to the 3/2, which is the limit as n goes to infinity of n to the 1/2 over n squared plus 1. Now remember, it's this divided by this, so it's this times the reciprocal, n to the 3/2 over 1. Okay. So when I multiply, I get the limit as n goes to infinity. And when I multiply these, I get 1/2. Remember, you add the exponents when you have like bases. So 1/2 plus 3/2 is 4/2, which is just n squared, over this times 1, which is n squared plus 1. And so this is equal to the limit as n goes to infinity. And remember, when you have a rational expression and you're doing the limit as n goes to infinity, all you have to do is keep the term with the largest exponent from the numerator and the denominator. So that's n squared over n squared. So I keep this term and I keep this term. And this just reduces to the limit as n goes to infinity. And that's just 1. So our limit is 1. So you can see it satisfies the conditions of the limit comparison test. This is a finite number and it's positive, it's greater than 0. So by the limit comparison test, that should be a 1, that the square root of n over n squared plus 1, see, the series that we compared it to converges, and since the conditions were satisfied from the limit comparison test, that this limit here equaled a finite number and it was positive, that means that this series here also converges. And that's the end of this video. Hope you'll check out my other ones. I'm going to do one more example with the limit comparison test. Hope you'll check it out. And if you like the videos, you can subscribe. Alright, thanks.